Very good morning. Welcome you all to the NPTEL course on Advanced Distribution System Analysis and Operation. And today we will look into the case study demonstration on transmission and distribution interaction systems. Now, when we talk about one of the case study in which we can demonstrate how transmission system and distribution system together can efficiently operate to not only accommodate the DRs, but also for the benefit of the customers, ancillary support systems, and let us focus on preventive voltage security constrained optimal power flow model for integrated TS and ADS. So, TS represent transmission system and ADS is representing your distribution system, that is active distribution system, and SCOPF acronym representing security constrained optimal power flow. So, we are very much interested to apply security constrained optimal power flow to a system which is transmission and distribution, active distribution integrated system. Now, first of all, try to understand the challenges. Increased penetration of distributed energy resources in active distribution system gives the rise in voltage violation due to their intermittent and uncoordinated operation. As you all know, because of intermittent distributed energy resources nature, which may penetrate more energy sometime and low energy sometime, which lead to voltage violations. Also, the retirement of thermal generators has led to scarcity of reactive power sources in the system, thereby challenging system security. Now, we are slowly eliminating the thermal power plants, and because they are no more existing, so the synchronous machine that used to generate reactive power and provide to the grid has also become scarce. Scarcity, that means a limited reactive power is now available to me due to unavailability of thermal power plants. So, dynamic reactive power reserve, that is DRPR, dynamic reactive power reserve, is an index for measuring voltage stability in the power system. So, when there is a sort of reactive power, then the voltage stability issues become significant. So, we need to understand what is DRPR to measure those dynamic reactive power reserve. Is it enough or it is sort of less available to the network for stability operation? Now, the motivation is mainly to system operators are advised to procure sufficient DRPR to avoid unfavorable scenarios in normal stressed and post contingency states. And then with the change in resource paradigm, these reserves from DRs have motivated the integrated TS-ADS studies for voltage stability. You all can refer the article by A. Sahu and D. Kiran et al., and that will give you more clarity on this simulation studies. Now, the N-1 transmission system line contingencies are included in the security constraint OPF model for the integrated TS-ADS collaboration. The large scale optimization model with normal and post contingency states is solved in two stages to handle the numerical difficulty. Stage 1, which computes the minimum DRPR requirement for the voltage secure operation of the integrated TS-ADS in each contingency state. The DRPR from stage 1 is incorporated into stage 2, which is the normal state of the integrated TS-ADS. It aims to minimize the system's reactive power losses and generation to safety the DRPR. In both stages, the integrated TS-ADS model is solved in a distributed way using the truncated diagonal quadratic approximation, that is TDQA algorithm, to respect their privacy. Now, in the stage 1, the DRPR for voltage secure post contingency stage, where in the stage 1 aims to procure adequate DRPR for the voltage secure operation of all the post contingency state, then moving to the maximum DRPR for each TS-ADS generator or DR over all contingency state of the equation 35.1 and 35.2 is the input for the stage 2, which is the normal state of TSO-DSO. So, that is what your 35.1 and 30.2, and these equations will be discussed more in detail. And please remember, DRPR is nothing but dynamic reactive power reserves. Now, in case of stage 1 DRPR for voltage secure post contingency state equations, we carry out this operation of maximization, where OR is representing your DRPR of TS generator at state M. MOR defines maximum DRPR to be procured for TS generator I. OR lowercase represent DRPR of ADS DR at state M. MOR lowercase define maximum DRPR to be procured for ADS. So, in both the equations, as you could see, when you talk about uppercase OR is for transmission system and the lowercase OR is for your ADS or active distribution systems. Similarly, the MOR uppercase is representing your maximum DRPR for transmission system and the lowercase MOR represents the maximum DRPR for your active distribution systems. Now, moving to the stage 2 after the optimization, the reactive power set point for securing DRPR, and the stage 2 aims to minimize the reactive losses and generation to meet the reserve requirement, that is MOR for transmission and MOR for the distribution systems from stage 1, ensuring a voltage secure post contingency state. So, what we normally do in case of stage 1, the data, the MOR for distribution, active distribution and transmission system is being communicated or shared with the stage 2, that is for your normal state, that is objective constraint and contingency states. Now, the DRPR requirement for the post contingency stage from the stage 1 is incorporated in stage 2 using equation number 35.3. It ensures that the DRPR of each generator is greater than the required for ensuring post contingency voltage security. So, once 35.3 is being achieved, then we get into the coupling constraints in equation number 35.7 and 8, and PB TS represent TS target of active power for active distribution system at state M, and PB ADS defines the ADS response for active power at state M, and Q is the TS target for reactive power of ADS, and QB ADS is the response for reactive power of the state. So, please try to understand, when you talk about the real power for both transmission system and active distribution systems, and the reactive power for active transmission system and active distribution systems are being taken care in equation number 35.7 and 8. The coupling constraints are given with above 2, where they are actually need to be a constraint for my objective functions. Now, the coupling constraint 35.7 and 8 is relaxed as a penalty using linear and quadratic penalty multipliers in the objective of TS and ADS model is given by equation number 35.9 and 10. So, you have objective function plus the constraints with a penalty multiplier that we describe in 35.9 and 35.10. Now, the transmission system and active distribution system are solved iteratively by communicating the information of the coupling variables, that is active and reactive power flow at the boundaries feeder, and penalty multipliers, that is alpha and beta, updated in each iteration of the equation 35.13 and 35.14 until the coupling constraints are satisfied. Once the security constraint optimal power flow solutions are available to me, then we can move to the overall model framework, where you could see that in case of stage 1, which minimizes the sum of DRPR of the TS generator to be procured for each transmission system contingency with a constraint of branch power flow generation, active reactive DRPR capacity limit, and then there is exchange, this is from TSO-DSO interaction, where in case of DSO, the objective is to minimize the DRPR of the DRs to be secure for each transmission system contingency with the constraints of power flow, DR active reactive, DRPR capacity and voltage security. So, all this information, the DRPR to be procured from transmission system and ADS generator or DRs will be provided to the stage 2 for post contingency voltage secure system. Again, the TSO try to minimize the reactive power set point deviation of generations and transmission system reactive power losses with constraints of branch power flow limit on the generation active reactive power, DRPR of the stage 1 and the line power flow. However, the DSO will try to minimize the reactive power set point deviation, DR and ADS reactive power losses with branch power flow limits on DR, active reactive DRPR from the stage 1 and line power flow. So, what it really means is that there is a two-stage solution with TSO-DSO interactions where for the post contingency voltage secure state, the information of the stage 1 will be transmitted to the stage 2. So, the two-stage preventive voltage security constraint OPF to by procuring adequate DRPR from the TS-ADS generation or DR, truncated diagonal quadratic approximation, that is TDQA, is used to distributed computation of the integrated TS-ADS problem. The active and reactive power flow through the boundary feeder is exchanged iteratively to coordinate their integrated operation. So, let us get into the resultant discussion for T30 and D33 system. So, we have chosen a transmission system of 30 bus and a active distribution system of 33 bus. So, as you could see, the 30 bus transmission system with ADS 1 and 2 at bus number 15 and 19. That means, in the transmission system, bus number actually 15 as well as 19, we connected those distribution systems of 33 bus. Now, as you could see that the two-stage preventive voltage security constraint OPF is implemented on a 30 bus transmission system connected with two 33 bus active distribution system at bus number 15 and 19. The optimized model is solved using a YLMP as the modeling layer and Gurubi as the solver on MATLAB. The original dispatch for the integrated transmission system and active distribution system is obtained from OPF by using MAT power. The voltage is limited between 0.9 to 1.1 respectively. Now, we have carried out three cases. Case number 1, where it is proposed two-stage preventive voltage security constraint OPF. Case 2, the DRPR is procured from the transmission system generators only and the DRs fixed. However, in case 3, does not procure any DRPR from neither transmission system generators nor DRs for the voltage secure post contingency scenarios. So, if you see the results for stage 1 with the DR support in case 1, the total required DRPR of the TS generator is less than in case 2 for all contingencies. For the most severe from line 12-13 contingency, which leads to the loss of generator 3, the total DRPR for cases 1 and 2 is 22.76 and 31.95 MBR respectively. The average DRPR over the 41 line contingencies is 6.43 and 14.17 MBR for case 1 and case 2. Now, you could see the DRPR procurement from DRs help in significant VAR saving for the system, which is as high as close to 55%. We can see the sum of DRPR of transmission system generators under 1-1 transmission line contingencies. Now, in case of case 3, as no DRPR are procured from the transmission system generators, in case 2, the transmission system generators have lower set point to reserve greater DRPR than in case of case 1 due to non-support from DRs for voltage security. The DRs maintain DRPR in case 1, so the ADS draw from actually reactive power of active distribution system to satisfy the reactive power need in the normal state. We can see the convergence curve for boundary variables in both stage 1 and stage 2. In case 3, No DRPR were procured for the post contingency voltage security. Due to this scarcity of DRPR in the system, the voltage at bus 8 fall below its minimum limit to 0.89 per unit, as it is clearly visible. Now, in case 2, due to the absence of support from DR, reactive power has to flow over longer distance, leading to an increased voltage profile as shown in figure 36.3. As you could see, there is a increased voltage profile which is almost more than 1 per unit all the time. Also, the localized supply for DRPR from DRs in case 1 gives the least system losses as shown in table 36.2. So, you can see in the case number 1, the P loss is 5.12, case 2 it is 5.47, in case of case 3 it is 8.54. So, this is the lowest compared to all the 3 different cases. So, with this we come to a conclusion of our case studies, and thank you for patient hearing. Bye-bye.